Good afternoon, my name's Catt. I'm a mechanical engineer working in Thales. So I'll give you a bit of background about the company itself and an overview of my presentation today. So quick chat about the company profile and some of the product lines that we work in, and then we'll go through some of the existing case studies that we've been developing and working on over the past number of years now. Quick bit of information about some of the materials and material properties that we've been working on in-house using some of our suppliers. Brief overview about our in-house additive manufacturing facility that we're building at the minute in Morocco, and then some of the future challenges that I expect that we are facing in industry in order to move this technology forwards. Okay, so the company profile itself, we're around the 60,000 employees mark worldwide. We're currently in 56 countries throughout the UK or throughout the world. It's a French company in itself, but we have markets in many other companies. Within the UK, we've got around about 10 sites spread out throughout the UK. I'm based down near Gatwick. We have sites across the UK there. The main point for Thales itself is we're very spread out in terms of our product lines. So we have business units within the aerospace and space divisions, of which additive manufacturing is playing quite a key part of that as it stands and in the future. We work on ground transportation, lots of things within the UK and abroad. We've got quite a big defence market, lots of things in the news that you would have seen in the markets there, and lots of our cyber and security side of things. So today this presentation mainly focuses on the space aspects of our business, as that's what we've published so far. But I'll touch on some things within the aerospace and defence side as well. Looking at some of our products, so Thales in itself, unlike GE or Rolls-Royce, we're not going to be putting additive manufacturing components inside jet engines or inside main high temperature, high strength parts like that. But what we would be using them for, what we are using them for, is for structural components and other components within some of our other systems. So some of our defence platforms and our satellites, the space side is mainly driving this. And then we go through other handheld equipment through to electrical items. So a lot of high power microwave amplifiers and avionic equipment down on the right hand side. So going on to some of our existing case studies, now these are some things that we publish over time here. Looking at one of our telecom satellites that we're part of here. Sorry, rolling back a sec. One of the things we've been doing is actually just taking, like our previous speaker said, going back to our first stage of the design and seeing where we can actually apply additive manufacturing rather than looking at redesigning parts based on this. So within this example here, we had identified a few structural components and some components with some key electrical characteristics that we needed to maintain. On this satellite as well, there's also some larger structural components and some complex assemblies. So two things there: if we're reducing the mass from a space point of view, we're reducing our launch fees by a great deal. It's tens of thousands of euros or pounds depending on where you're working. And then from a design point of view, if you can combine components, as our previous speakers have alluded to, then you can save on your design cost, you can save on your qualification cost and time. So with those two things in mind, we're looking at saving mass and the cost of our products here. So this is one of the early examples. This is a titanium part. If you look in the top right hand corner of the screen, these are some dishes on here. Now underneath each of these dishes there are 8 of these smaller components. But each component, although it looks the same, the picture on the bottom left there are actually 8 different designs for components that attach the dish on the top right to the support structures below that. So for us to go and machine 8 different components or to cast parts in order to get the complex shapes that we've got here, it's a lot of additional work for us to do. Now, if you imagine, we're not making hundreds of satellites, we're making 2s, 3s, but on this satellite itself, in this picture on the top right, there's 2 dishes, so there's 16 parts that we've used here to save weight and some cost on here. On top of that, if you look at the lead times that we've saved on here, using additive manufacturing in the correct way, we can produce these in 3 weeks for 8 parts. I haven't got the figures for what it would take from a machining and casting point of view for this example, but this is a piece that we're using to provide some initial qualification data whilst we're working with our suppliers here. So again, touching on the optimization slides that we've covered before, this is looking at optimizing the structure on the left-hand side. It's a microwave component, so there's a couple of microwave horns pointing up to the top left-hand side of the screen, and then there'll be 2 rectangular waveguides coming out the back of those horns. So what our design team had to do is define the space needed not only for that waveguide to fit through, but also for the team to install the waveguide within that section, which forms the grey box in the top left. Then, over a series of iterations, as the speakers have talked about already, we end up with an optimized design, which we can then import back into our CAD program, remodel, forming the design on the right-hand side. It then goes through its our normal design validation process and an extensive amount of testing here as well. So something with this is the largest SLM, selective laser melted, part that has been qualified for space flight that I'm aware of within Europe. It's something we developed out in France with Thales aerospace, one of our parts business units within the company, and it's due to be launched into orbit later on this year or early next year. These will be on 2 satellites, so again, it's not really high quantities here. To give you an idea of the cost involved with that, so we're really at the low end of quantity here. Going back to the other points, we saved around 20% on the mass, which, okay, perhaps you could save some more, but again, the mass is a key driver on the cost of our launch fees and the cost of these parts. It's quite a good saving there. As it's said, and as has been said before, it's quite low heritage with these systems, so it's quite costly to validate these parts. In this example, 2 of these just about fit within the machine that these are printed on. One is destructively tested, the other one's inspected and has some other validation done on it. So for every one we fly, we need to build 2, if you like, as it stands. Just going over some other examples of other areas, this presentation mainly covers the metal side. We've done quite a lot of work on tooling to save on our production costs. Lots of prototyping work as everyone is now doing within the industry. We're also using SLM for some cast parts as a initial prototyping, if you like, whilst we're waiting on the other parts coming out of the foundry there. So moving on to the second half of this presentation, I'm going to share with you now some information that we've been doing on materials testing. Now, these are just some results that were published in the paper before by one of my colleagues. So to date, we've conducted a lot of tensile testing on a number of different materials on the list on the side, from FDM, SLA, SLM and EBM processes, along with some others which I won't go into today. What I'm going to talk about now is some results of our high cycle fatigue testing. Now this is a bit more involved than just the tensile test. It's repeated over a length of time and involves these little dumbbell tokens, or test samples, sorry, in the bottom right. So the idea of this, these data points would give us the information we need to generate this SN curve, this Euler curve. Our data points would be above the curve, and our design space, if you like, would be below the curve, for those of you who aren't too aware. As part of this testing, we've noted a number of defects. They're categorized into 3 different areas, as we'll go on to in a minute. The ones here are porosities, which you'd see in similar cast parts. surface defects, so cracks or unmelted areas of powder on the surface of the components. Unmelted zones within the component, so as we're looking at this image, this is, if you imagine the z-axis, so the layers, you're looking at a slice through one of the layers that's failed. So you see the small little circles within that pocket there, that's some unmelted powder due to some problems with the manufacturing process. Similarly, if we're looking kind of through a layer rather than onto a layer on the right hand side, you can see another area where there's some unmelted powder there. This has given us a whole load of data that's been collected over quite a long time now. There's a series of dots and triangles which show SLM and EBM results. And what this shows us is that actually, as long as you get the right supply and the right processes, SLM for this material seems to be comparable to EBM, the same thing. So when we compare these to published data for cast and wrought parts, we get these two charts here. And again, as long as you get the right processes in the qualified stance with your supplier, you could achieve the same material properties of that of cast parts within titanium from what we've found on our data here. So what I'm going to show you now is going on the defects that we looked at in a couple of slides ago. This gives us a few areas where the defects seem to be the main failure. So if you look at the green area down at the bottom left, most of these defects were noted as, or most of these failures were due to surface defects on the test samples. Now these test samples were as-built samples, so there wasn't any post-machining or polishing on there. The area in the center, this is mainly down to unmelted zones within the part, so more to do with things you can't see from the surface or through penetrant inspection. And then in the top right, we've got failures due to porosities at really high cycles. So again, looking at the defects there, these are the three key areas. So the main one would be surface defects. If you know you've got an area that's critical to the strength of your part, you could look at polishing or machining the surface in that area to remove these. Then the next failure tends to be unmelted zones or unmelted areas of powder within the parts, and then porosities as well. Turns out that from what we found, big porosities are more critical from or causing an earlier failure, even though they're right up on the far right hand side of the chart we saw earlier on. But at the same time, if they're close to the surface, they're also more critical. So when you're doing your analysis of your parts in the qualification stage, these are some of the things we found that we need to look for when we complete our scanning. So this is something that was just a bit of interest from my side. This is some in-situ testing or inspection during a tensile test. So here we have a machine that can monitor our parts during a tensile test. If we zoom in this area, we'll see our little test sample on the left next to our lovely £1 coin, maybe not, euros. And the test sample is just in the center there. So during our tensile test, you'd hear some pings or some clicks, and that would correspond to a drop in the curve on the right. So this is a scan of the cross-section of our test sample, the red circle in the bottom right. And as we go through, we can start to see these defects start to appear. So if we jump between these slides, you can see the cracks start to appear in here, which is quite a good indication of where some of these defects were coming from. It was just a nice thing to see from my side of things. So quickly to wrap up, this is released as part of a press release. With a new facility that we're developing over in Morocco, we've decided to take some of the manufacturing in-house in terms of 3D printing side to ensure that we remain quite a key player within the additive manufacturing technology. Can't say too much else about this as it stands, but there is a press release online. Moving on to future challenges. So the main things that we foresee as some future challenges in our industry and things that would help us through our technology is to look to see if our machine manufacturers can look to increase the build envelopes of some of the main processes to allow us to build larger parts and combine more components. We're looking at incorporating more complex assemblies and moving assemblies into one build, and we're also looking at new materials which we can use within our parts here. That's a bit of a summary there. Okay, that's all I've got to say today. Thanks very much for your attention.